Halleluja, ek's in.
Is that it?
Ja.
What's it? Thank you.
Dat everyone gets a name, good. Dat ik creëer some more.
1, 2. 1, 2. 1, 1, 2. 1, 2. 1.
Is anyone that I can invite to this call?
1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 1, 2, 2, 3. 1, 2, 3, 4, 5, 6, 7, 7, 7, 1. Good. One, two, three, 4, 5, 6, 7, 8, 9. So, good morning, everyone. Welcome to this summer school. Yeah, the weather is not really summery, summery, but it should turn to the sunny in the next couple of days. I think from Thursday onward, it should be sunny again. Yeah. Now, I would like just to start by explaining to you why we call it summer school, although we're not in summer anymore. Yeah? Because traditionally, this Chris Engelbrecht summer school happens in our summer. Yeah? And so it was supposed to be this year. We had a technical complication that the university is renovating our offices. So we didn't have access to our usual seminar room. Yeah? And then we had to do a few compromises to find an appropriate venue for this event. Yeah? I think I might have interacted with most of you or some of you yesterday evening. My name is Francesco Petruccione, and at the moment, I'm speaking to you in my capacity as the director of NITEX. Yeah? So I will take the liberty just now to, for those of you that maybe don't know what NITEX is, to explain it briefly, and then I will put my other hat as normal quantum guy and speak about something else. Yeah? Maybe before we start, we have maybe some logistic things to sort out. Yeah? If we will have our coffee breaks out there, but our lunches in the main house, in the main STIAS venue. Yeah. So hopefully by lunchtime, the rain will be over. The restrooms are just, you go to the coffee area, turn right on the corridor on the outside. Yeah. All of you should have received with your name tag a voucher for the dinners that we don't have here. Yeah, which is, we have a braai, I think, for Thursday or Friday, yeah. So the other evenings, you probably already discovered the student center of the university, which is just down the road from here. And with that voucher, it's a kind of a big food court. You can go wherever you want and eat whatever you want. Yeah. And it's valid for 3 years. So even if you don't spend it now and you come back, you can have a coffee maybe next year if you come again. Yeah. Outside, we've put the kind of a register that we need for our sponsors. Yeah, they want to know that there were actually people in here and not just avatars or otters or whatever. Yeah, things that go into your meetings these days. Yeah. And is there anything else, Graham and Rene, that we need for the logistics?
You're welcome.
Yeah, as I said yesterday, if there are problems, go to Graham. If you're happy about everything, come to me. Yeah, so that's the division of labor. Yeah, the fair division of labor. Yeah. I might have it. Yeah, and the register is just outside. So next in the coffee break, please put down your name. Yeah. Yes, sorry. Thank you very much. Yeah, and yeah, now we can use that for the questions. Yeah, perfect. Thank you. No, sorry, that's I will mention it just now as well. Yeah, that we also broadcast these lectures, yeah? Like everything that we do. So let me start with a short 10 minutes introduction to NITEX. Yeah? We had in South Africa since 2008 a National Institute for Theoretical Physics. Yeah? That was National Institute by name, but technically administered by our National Research Foundation as a center of excellence. Yeah? And center of excellence, centers of excellence can only survive 3 times 5 years. Then a sunset clause kicks in and it's game over. Yeah? But NITEX was fairly successful. And so with the Department of Science and Innovation, Science, Technology and Innovation now, a whole procedure was set up to see if there is a scientific case to save it somehow. Yeah? And usually the strategy is if you can't survive small, maybe you can survive big. Yeah? So this new institute was set up as the National Institute for Theoretical and Computational Sciences, yeah, with 4 pillars, which are research, training, engagement, and getting the African continent involved. Yeah? And to make it bigger, this was the strategy. Yeah? We are no longer an institute about theoretical physics. We are also about mathematics, statistics, astronomy and astrophysics, quantitative biology, including bioinformatics, quantitative finance, Earth system and climate change modeling, and data science. Yeah? The only basic science that is missing, for whatever reason, is chemistry. Yeah? But, you know, the borderline between computational physics and computational chemistry is a little bit porous. Yeah? Anyway, so we are this multidisciplinary and multi-team institute, and I like to call it a pan-disciplinary institute because since we are mainly a research institute, we put at the core the challenging questions, yeah, and we don't really care about the disciplines that people traditionally belong to. Yeah, we want just people to work together to solve big problems. Yeah, so. To make it work, the basic recipe is that we embrace open science 360 degrees. Yeah? All aspects from data or sources, software, and so on and so forth. Yeah? And also in these days, we also engage also with ICTP in fighting for open access to computational resources. Yeah? You know, we don't have the 200,000 GPUs that Elon Musk buys for breakfast. Yeah, we have much less. Yeah, also open codes. Yeah, open source. But now, even more important, open weights. Yeah, not all of us have the computational capacity to train a large language model. Yeah, so we want at least models where the weights are open and freely accessible for playing around. Yeah. And what is really very important, and this I say mainly not for you guys, not for the speakers, for my colleagues, yeah, that we are not a funding agency. Yeah, so this is one of the categorical statements of our Department of Science and Innovation. We need to really act as a research institute and put money in our research activities and not make calls for random things. Okay. So, what does this? Sorry, it's a bit. There's a bit of a delay. Yeah. So we are NITEX is a consortium of all public universities in South Africa. Yeah. So all of you are part of a NITEX branch. Yeah. We organized in 5 nodes. I will show you the nodes just now, and in the nodes there is a collection of branches which are all the universities in the country. Yeah, this is how we are structured. Yeah, we are in the hub, Stellenbosch, yeah, but then we have a node in the Western Cape, for instance, with UCT, AIMS, the Cape Peninsula University of Technology, University of the Western Cape. And there are further 4 nodes in Gauteng, KwaZulu-Natal, in the North, Eastern Cape, and Free State. Yeah, but the point is that every university in the country is part of NITEX, and you are sitting here at the hub. And here's, just for curiosity, how the university in South Africa are distributed. Yeah, you see there is a high concentration in Gauteng, around Johannesburg and Pretoria. Yeah? a fairly large concentration in the Western Cape, in KwaZulu-Natal, Eastern Cape, and then scattered at least one university in the other provinces. So this is how we are organized. So Stellenbosch is the hub, and then we have 5 nodes, and the 5 nodes include the branches. At the end of last year, we had a network of, let's say, around 350 associates scattered across these 26 universities. The majority of them, this peak is sitting in Stellenbosch. And then, some universities are just maybe a couple, but that needs to change as we grow. So the distribution of the university reflects also somehow the distribution of the associates per province. I think in the Western Cape, we have the majority, we have 118. In Gauteng, it's also 100, the number, where is it, 113, yeah? So more or less the same numbers, and much fewer in other provinces. We started as an Institute of Theoretical Physics, yeah, and this is the distribution of the associates per discipline, yeah. And you see, we are no longer a theoretical physics institute because theoretical physics is just maybe just above a third or a quarter of the associates. Some disciplines are catching up nicely, yeah. The mathematicians, data science have embraced NITEX quite strongly. Others are catching up. But there is also a difference in, for instance, statistics is not a particularly popular discipline. There are not so many statisticians in the country, so there is only so many that you can recruit. Yeah, we have a few international links with ICTP, with a cluster of research excellence between ARUA and the Guild. These are our our current 10 research program. You see, it goes from quantum technology to disease control and health, to quantum gravity, to quantitative finance project, mathematical structures, computational modeling of functional materials, complexity in biological system, Earth system modeling platforms, the usual machine learning stuff, and computational and theoretical astrophysics and cosmology. Yeah, so those are welcome. Sorry, probably now we are probably complete. Yeah. So these are the 10 current research programs for the current 5-year period. Yeah? And that's where most of our resources go at the moment. Yeah. What is sorry, there's always a little bit of a delay when I change the slides. And because I've lost the Zoom connection. Sorry. I lost the Zoom connection. Let's see. Sorry, Zoom is reconnecting. Let me see if we can start again. No. Yeah, okay, I'm back. Sorry, I think the internet is not particularly stable. Yeah, okay. Now, what is also, sorry, that's not me. Yeah, might be of interest to some of you. Yeah, is that how the universities are involved in the various research programs. You see, there are some usual suspects like Stellenbosch, UCT, UP, Northwest University, and UKZN that are involved essentially in all research programs. Yeah? And others, you see some universities that in South Africa we call historically disadvantaged institutions. They're not yet really involved, and we need to work harder to bring them on board. Okay, that's maybe boring. This is mainly for the younger semesters here in the audience. Yeah? Some of the things that we do besides research, yeah, we offer always every semester honors master's level courses in various topics. Yeah? For instance, at the moment, these are the topics that we offer this full semester course. And you see it goes from health insurance mathematics to integrable systems. That's and everything in between. Yeah. So if some of you are not aware of this, please go on our website. You will find all the details of these things. Yeah? Maybe for a semester, just 1 year younger than you guys here, we have internship programs mainly aimed at honor students. Yeah. No, I say that so that maybe when you go back to your institution, you can advertise a little bit and become ambassadors. Yeah. And every year we have around between 20 and, sorry, again, it doesn't, have I lost the connection again? This is very painful. Yeah. No, the internet is on. Sorry, this is very painful. Where is my Zoom? Now my Zoom died. Where is Zoom? My Zoom died. Yeah, yeah, please. The internet. Pathetic here.
I think it's pathetic. He was saying the internet.
Yeah.
Do you want to bring that thing closer?
It's going to be a whole swap. Francisco, if you don't connect you now, then we can make a plan. It will take 2 minutes.
Yeah, let's see. I think it's reconnecting to something.
I can leave my phone here, then you keep this connection. Maybe.
Damn, I lost my Zoom completely.
Go to your email and connect on my email.
That's so. Okay, so this was the internship program, yeah, that time might be interesting. And the idea is to increase the mobility. So we want people to do the internship not at their own university, but somewhere else. Yeah, so to increase the connection and maybe help them find co-supervisors for their honors projects or something like that. Yeah? Maybe interesting to you guys. We have also a bursary program for masters and PhD students, yeah, and for postdocs later. And every year we have around 30 students between masters and PhD students that we support. Yeah, so when the next call of NRF bursary comes out, you can click NITEX, and it should maybe increase your chances of success. Yeah. Some of the standard things that we do is, for instance, this summer school. This is already in the 33rd edition. Yeah, this one I think is the 33rd. So it started long ago, and it was traditionally always theoretical physics, and we keep it like that. Our plan is to slowly, when finances allow, to include other summer schools in the other disciplines as well. Yeah? So that we do everything more or less equitable. In January, we have traditionally a summer school with our Center for High Performance Computing, which is mainly a week of programming, yeah, and a week of scientific computing, yeah, with Python, and that is a very popular one because we have around 850 participants. Yeah? I will say something about that just now. Yeah? Here it is. Yeah? So the model that we used for this programming coding summer school is a kind of a hybrid distributed event. Yeah, we want students to come together in a venue at the university. Yeah, some of you might have participated. Yeah, and we broadcast the lectures and we provide tutors, coffee breaks, lunch breaks, and this is the model that we try to adopt for everything we do. That's why we are broadcasting this lecture as well, to give other people that can't be here because, you know, there are financial constraints. Yeah, but at least in principle, the possibility to follow what we do. Yeah. And you see, when we started the summer school, it was a school like this. We had around 50 people or so. Yeah? And the moment we went online during COVID, we increased the numbers to, let's say, the 200s. And when we started the hybrid model, we started reaching 800 plus students in one go. Yeah. So this is really a model that works very nicely and that we want to perfection it in everything that we do. Yeah. Every month we have a mini school. So every Wednesday afternoon, there is a double lecture dedicated to one topic. This is just what we had last year. Yeah? So Graham gave us a mini school introduction to quantum thermodynamics. We had courses on parallel computing, blah, 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 on quantum chemistry, on quantum computers, and sort of everything in between. Yeah? We have also a weekly colloquium program. Yeah? We had one colloquium yesterday, just before our reception. Next Monday, we will have a special colloquium because next Monday will be World Quantum Day. Yeah, so if some of you are still around, you're welcome to attend that as well. And you see lots of other activities. Essentially, every week we have several things running. Yeah? We started last year something very nice, which we call the micro school. Yeah, we just 20 minutes every Friday at lunchtime. Where it's intended as peer-to-peer, students to students, where students just share in 20 minutes a skill that they learned that they think is useful for their studies and to others. Yeah, and that goes from from Matplotlib to I don't know, to things that I don't know what they are. Yeah? LNCR loop. I have no idea what it is personally, but apparently it's very useful. Yeah? So one day I will watch that as well. Yeah? So, and please, if you have any skills, just reach out to us and we put you on the program. Yeah? Everything we do ends up on our YouTube channel, where we have already, probably by now, 650 videos. Yeah? But what is really nice is that we have around 12,000 watch hours, not just clicks, just time people have watched the videos. Yeah? And I think it's an impressive number. That means that some of the videos that we record are useful, yeah? and people watch them. Okay, this was the short introduction to NITEX. Yeah? Do you have any questions? Yeah, please.
The internships for honor students.
Yeah.
Just like the master students as well.
No, the internship is mainly targeted at honor students. Yeah, and the original intention was there to help people find a co-supervisor for the honors project, mainly in case they want to do an honors project in something that at their own university is not so prominent. Yeah, so we want to help them engage with others, and that very often leads to master's thesis and so on and so forth. Yeah, but that's targeted mainly at honors students, mainly because so far we don't have a program, a bursary program for honors students, yeah? Which might be something that we will introduce at some stage. Yeah? In the past with NITEP, we didn't have it because what we realized was that we had it at some stage, that students do an honors in theoretical physics and then they end up doing the masters in mathematics. Yeah? And then from the NITEP point of view, it was not a good investment. Yeah? Now it doesn't really matter, because even if you do your honors in mathematics and you end up doing your masters in data science, it's absolutely fine. It stays within the family. Yeah? So that's something that, as the budgets permit, we might reintroduce. And then maybe we might reconsider the internship program as well accordingly. But at the moment, the internship program is just streamlined for honor students. Yeah. Any other question? No? Please. Yes, please, so that the people online can hear you as well.
Should be. Okay. I want to know that quantum Q South Africa from
Yeah.
Q World is still part of the family.
Yes, 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 yes,
Okay.
yes, yes. We organize. We are a Q cousin in the Q thing, and we organize regularly those Q bronze, Q silver, Q whatever courses. Yeah.
Oh, okay. I wanted to know that.
Thank you. Any other question? No? Okay, then do you want to do 5 minutes break or should I just continue?
5 minutes break.
Okay, we can have a quick 5 minutes coffee, yeah, and then we can continue. Yeah. Hank. Okay, excellent. Then let's start again. I thought this morning, just to bring us all in the mood of the school, and considering that we are in the International Year of Quantum Science and Technology, and next Monday is World Quantum Day, and in 2025, because of this, every day is Quantum Day. Yeah. Yeah. So happy Quantum Day today. Yeah. And I thought I digress a little bit and just slowly bring you in the mood. Yeah. So just in February, a few months ago, not so many weeks ago, yeah, at UNESCO in Paris, the International Year of Quantum Science and Technology was started, and the idea is, you see, to activities at all levels aimed at increasing public awareness of the importance of quantum science and applications. Yeah, so that's what we are trying to do this week. Yeah, and convince more people to start working in quantum science and and technology. Yeah, and if you go on the website, you see these are the aims and the mission of the year. Yeah, so. I think this week we should focus on the have fun part. Yeah, so learning new things in a inspiring framework. Yeah, and again, if you go on the website quantum25.org, these are the things that quantum science technology promises us to achieve. And you see it goes from health and well-being to clean energy and everything in between. And we will hear about some of those things. For instance, Barry will speak about quantum sensors and things like that, they appear here, they appear a little bit everywhere. Yeah? And others will address other potential applications. So what I wanted to do now, maybe in the next half an hour, 40 minutes, yeah, between now and the official coffee break, just give you a little historical introduction. Yeah? Maybe because we know that not all of you are primed as quantum scientists yet. Yeah, next week you will be, but not yet. Yeah. So this atomistic quantum thing started, again, there's a bit of a lag. Yeah, started long ago. Yeah, a 5th century before Christ, there were already people that were considering what the world is made of, and they thought maybe it consists of something like indivisible atoms and the void, yeah, or empty space. Yeah. And so the tradition goes back a long time. Of course, at that stage, it was just ideas, yeah? And not really equations. Yeah? It continues, more or less at the same. What happens? It's very slow. Yeah, the reaction time. Yeah, just moving around a little bit, a century in times. Yeah. And people like Democritus really tried to systemize a little bit the picture. Yeah. So with statement like everything is composed of indivisible atoms that move in the void, like we saw before. Yeah. But then with a different touch. Yeah. With the realization that atoms might differ in shape, size, motion. Yeah. And that is the cause for the different states of matter that we see. Yeah. I mean, that's not bad, considering it was so long ago. Yeah. Yeah, the story continues. Yeah, and in Greece and in India, yeah, with similar tendencies. For instance, this Vaisheshika school, 600 years before Christ. Yeah, they also had different classes of atoms. What was very nice, they thought atoms are spherical. Yeah, so all of a sudden symmetries come and seem to have to play a role. Yeah? But also other things that atoms combine in fixed ratios, yeah? Form larger structures. Yeah? There's also, considering they didn't have a microscope or any major chemical expertise, that's I think is quite impressive. Yeah. And of course, on the other side, Epicurus also starting, those discussions that continue to the day. Yeah, the role of quantum physics, free will, and so on and so forth. Yeah. So you see, all these things have kept people busy for a long, long, long time. Yeah. Things, it started very optimistic, the quantum theory story, yeah? But then some guys, like these two gentlemen, sort of didn't like the idea, yeah? And they preferred a more continuous picture of the world. And for more than almost 2,000 years, atomism was almost forgotten. Yeah, and people probably got burned alive for believing such things. Yeah? So you were at least considered heretical in at least in certain religions, in certain continents. Yeah? So only in the 1600s, yeah, people started a revival of atomism, yeah. And this gentleman that maybe is not so famous, yeah, but I think he had a very strong influence in the conceptual development of things, yeah, because he tried to Christianize atomism, yeah, to make it more palatable to the church. Yeah? And the trick was to say that atoms are created by God, yeah, and then the church was happy, yeah, and we could do quantum theory without being killed. Yeah? So and this was important because this influenced people like Descartes, Newton, and so on and so forth. Yeah? Of course, Newton. Now we are on solid ground. Yeah. Not only atomism, but also the assumption that light is formed by particles. Yeah, so that's also a very important step in our conceptual building of theories. Yeah, and then the first quantitative approaches. Yeah, where essentially trying to couple maybe thermodynamics with atom theory. Yeah, in first attempts. Yeah? So this was just very brief kind of historical overview. Yeah, and then it all started, yeah, and these are the things that I will just browse on it because this is probably you all know from your first year physics lecture. Yeah, it started with Planck and the famous ultraviolet catastrophe problem, yeah, where people were not able to explain using classical physics what was going on. Yeah, and Planck came up with his famous postulate that energy is emitted and absorbed in terms of quanta, and this famous formula equal h nu, and h still bears the name of Planck. And in 1918, he got the Nobel Prize for this. From there, you see, you recognize the same h nu equation. Yeah. Einstein explained the photoelectric effect, also using the fact that photons are quantized, and 3 years after Planck, he got his Nobel Prize for the photoelectric effect. Yeah, and all his other discoveries are for his services to theoretical physics, yeah? Special relativity, general relativity, and so on and so forth. Yeah? So then This is more or less the beginning of more modern quantum mechanics. Bohr came up with his Bohr model. Yeah, the problem was that, you know, if you think of the atom as a nucleus and the electrons flying around on circles, you have obviously the problem that the electrons radiate energy and they should fall in the center. Yeah? But that's not what you observe. Yeah? And so Bohr came up with the idea maybe the momentum, the angular momentum is quantized. Yeah? And again, the H appears on the right-hand side, yeah? The famous Planck constant, yeah? Or in this case, H over 2 pi. Yeah? And he was able to explain the spectrum of hydrogen and so on and so forth. Yeah? And again, 2022, Nobel Prize. Yeah? Quite a strong succession of Nobel Prizes. Yeah? But this model, of course, works fine for hydrogen model, it doesn't work for everything. Yeah? Another important step was just a few years later, the Broglie, yeah? With the wave part nature of particles and matter waves. Yeah? So the idea was that even physical particles can be interpreted as wave, yeah, and the connection between momentum and wavelength is the famous formula that still bears his name. Yeah? And he was very, very lucky, Nobel Prize in 29, because a few years later, this was part of his PhD thesis. So please try to follow in the steps of this guy. Yeah? His theory was confirmed experimentally, yeah, and that's the best thing that can happen to you if you want to get a Nobel Prize as a theoretical physicist. Yeah? You need someone to do the experiment and validate. Yeah, the reason why. Sorry, mi era si può votare. Why 2025 is the International Year of Quantum Science and Technology is because proper quantum mechanics started in 1925. Yeah, with people like Heisenberg that formulated the famous matrix version of quantum mechanics. Yeah, and it's very nice, this quote of him where he says, everything is still vague and unclear to me. Yeah. But it seems as if electrons will no more move on orbits. Yeah? So the picture of electrons following circular orbits around the nucleus was officially dead. Yeah? And the picture that we still have of quantum mechanics essentially holds. And those are the famous Heisenberg equation of motions for observables. Yeah? And he was also very lucky just a few years later, 1932, he got his Nobel Prize. Yeah? Around the same time, Schrödinger, but I think his paper was published in 1926. Yeah? Yeah? He came up with a famous wave equation, yeah, that we all know, and that is still at the core of everything that we use. Yeah? And he was not so fond of Heisenberg's approach. And in fact, he says, now the damn Göttingen physicists use my beautiful wave mechanics for calculating their shitty matrix elements. Yeah. And, you know, and still to today, some people like the one picture more than the other one. Yeah? And probably similar statements are made on a regular basis. Yeah. Okay, anyway, he got his Nobel Prize in 1933 for the discovery of new productive forms of atomic theory. Yeah? And the new productive form is the famous Schrödinger equation. Yeah? That still bears his name, of course. Yeah? So people had the equation, but they didn't really know how to interpret it. Yeah? And that's where Born came in, yeah? Who came up with the famous statistical interpretation, putting the square of the wave function, interpreting the square of the phase function of the wave function as a probability. Yeah? And at the same time, coming up with the idea of what we still call the measurement problem, the collapse of the wave function when you measure it, and the probabilistic outcomes that are still crucial. For instance, you'll see later in quantum computing, it's still the same problem. Yeah? It's still so, and he had to wait a bit longer for his Nobel Prize. Yeah? He only got it in the 50s, yeah? For the statistical interpretation quantum mechanics. So these were the fathers of quantum mechanics. And, you know, we want to discuss here the theoretical foundation of quantum technologies. Yeah? The same happened for this first quantum revolution. Yeah? That after, you see, in the 20s, in the beginning of the century, Planck, Einstein, really fundamental stuff. In the 20s, the formalization of the theory. And then it took another 30 years until the first really groundbreaking technological applications were developed. Yeah? First the transistor, then lasers, diodes, microprocessors, MRIs, and things like that. Yeah, so there's quite a gap from here to technology. Yeah, so that, you know, the first quantum revolution essentially induced what people now call the third industrial revolution. Yeah, everything that happened essentially after the invention of the transistor, yeah, until maybe the 80s or so. Yeah. But now, okay, sorry, maybe let me, yeah, okay. I mentioned the laser that also led to a Nobel Prize. Yeah. Here, the inventors of the transistor, yeah, also led to a Nobel Prize. Yeah. Superconductivity. Sorry, I didn't mention it on the slide before, but that's also something very critical. Yeah, and there's a bit of an overlap in Nobel Prize winners here. If you look at these three gentlemen, one of them you recognize on this slide as well. Yeah, so that there's also that possibility, and it was really important to show that quantum mechanics can also have effects at a microscopic scale. Yeah, not only at a microscopic scale. Yeah. And then, of course, other inventions like atomic clocks, GPS, and so on and so forth. Yeah. But in this school, you're more interested in the second quantum revolution. Yeah. Yeah, and this is something that maybe started in the 80s, yeah, with people like Hans Dehmelt, yeah, that for the first time were able to show that we can trap single ions and observe them, yeah. So what you see there in the graph on the right is the photon count, yeah. If photons are emitted, it's at the top. If photons are not emitted, it's at the bottom. Yeah? So you could really see with your naked eye whether an ion was emitting or absorbing light. Yeah? And this was really important because it was the first time in history that we could manipulate single atomic particles. Yeah? Up to then, quantum mechanics was just, an ensemble theory. Yeah? Nobody had ever manipulated a single hydrogen atom. Now, what you had in your textbooks was just a mathematical exercise. Nobody had really mathematical. So this changed dramatically in the 80s. Yeah, first with ions, then with cold atoms, and so on and so forth. People like Sir Sharrock and David Wineland got a Nobel Prize in 2012. Yeah, exactly for groundbreaking experimental methods enabling, measuring, and manipulating individual quantum systems. Yeah, and this was a little bit the turnaround time for the second quantum revolution. Yeah? The ability to manipulate single quantum particles, yeah? Being atoms or particles of light. Yeah? Yeah, and this is when all the spooky things of quantum mechanics. I didn't speak about entanglement and things like that. Yeah? But all those spooky, wavy things of quantum mechanics all of a sudden became technology. Yeah? And just a few years ago, Alan Aspect, John Clauser, and Anton Zeilinger got a Nobel Prize 2022 for experiments with entangled photons, yeah, and pioneering quantum information science. And and technology essentially. Yeah. So all the crazy non-local properties of quantum mechanics started to become technology. Yeah. So that what we experienced over the last decades essentially was the merger then from quantum mechanics and information science. Yeah. So forming what some people now call quantum information science, or where we essentially mean all the storing, processing, communication of information just using quantum physics. Yeah, and the ultimate goal is to build a quantum internet, yeah, with computing, communication, and metrology and sensing as the building block, but also other applications that we will also hear something about, like quantum biology and things like that. Yeah. Okay, let me skip this. So the core of the second quantum revolution are essentially quantum metrology, sensing, quantum communication, and quantum computing. Yeah, so these are the three pillars, and hopefully we will cover a little bit of everything. Let me skip these things here now, because I think I'll speak too long here. Back when we were in Durban, more than 10 years ago, we started working on quantum communication. Yeah? And in 2008, 2009, we had a quantum communication network on the optical fiber network of the city of Durban. Yeah, yeah, and in 2010, for a little while, we were quite famous because we did QKD between the risk management center of the FIFA World Cup stadium in Durban and the police risk management center outside. Yeah, and that was really real life link. Yeah. So, and it worked, otherwise they would have killed us. Yeah? And for a little while, we were all over the news. Yeah? So I mentioned that the ultimate goal is quantum, that kind of a quantum, a secure quantum communication internet. Yeah? And several years ago, China started leading quantum communication via satellite. And just a few weeks ago, we published a paper with Nazir and many Chinese colleagues where we established a quantum satellite link between Beijing and Stellenbosch. Yeah, so and that was really very, very nice. Here are some picture of the roof of engineering. Yeah, and because we managed to have the longest quantum satellite link that has ever been achieved, and second, also the highest rate of key transmission in real time that that was ever achieved via satellite. So we are very proud of that, and if you want to know more, Nazir can tell you everything about it. Yeah, so now, no, I told you 80s was a little bit the critical time for the transition from the first to the second quantum revolution. Yeah, and that was also the time where people like Richard Feynman started thinking about the potential use of quantum computers to solve quantum problems. Yeah, because if nature is quantum, a quantum machine should be able to model it easy. Yeah? And very few years later, David Deutsch in Oxford, he came up with the universal quantum computing model. A little bit what Turing did for the classical computer, David Deutsch did in principle on paper, yeah, for the quantum computer. But it took another 10 years until people like Peter Shaw came up with the first useful algorithms. Yeah? So, for instance, the most famous algorithm of Peter Shaw is the factorization algorithm, yeah? Where you could really see that for a useful algorithm, there is in principle an advantage in having a quantum computer. Yeah? The same Peter Shaw also gave us the first quantum error correction code, yeah? Which means that, if you want to build a quantum computer, you need to have some error correction procedure like every classical computer has as well. Yeah? So you could in principle say that he gave us the first algorithm and the rest to build a fault-tolerant quantum computer. Yeah? And since then, many, many more algorithms have been developed. And in recent years, a few claims of quantum supremacy, of quantum advantage, of quantum utility, quantum practicality, yeah, have been continuously made, and we will hear something later probably about quantum machine learning in one of the courses at the school. Yeah? The reason why people are so excited about quantum computers, algorithm, yeah, you see on this in this slide where we compare the classical algorithms and the quantum algorithms complexity. And if you compare the same class of algorithms, you see that on the right-hand side, there are lots of square roots and logs. Yeah. And those are essentially your speed up, yeah, either polynomial or even in some cases exponential. Yeah. And the same, for instance, here for specific, come turn. Okay, doesn't want to turn. Okay. Okay, anyway, for other mainly quantum machine learning algorithm where you have the same, sorry, go back. Yeah, the same problem. Yeah, that on the right-hand side, you have lots of square roots and logs. Yeah, and now I think there is always a little bit of a delay. Come. Why doesn't it go? Okay. You know, what are we supposed to do with these quantum computers? Yeah? Since a few years, we have also hosted by CERN an Open Quantum Institute, yeah, and they try to promote test cases in which to prove that quantum computers can really make a difference. Yeah, and one of these problems for me is to develop a new carbon capture materials. Yeah? Other problems, for instance, tackling antibiotics in wastewater. Yeah, all problems that cover several of the sustainable development goals. Yeah? This is also a very important one, eco-friendly fertilizer production. Now, you know, to produce fertilizer is very energy intensive. You need high temperature, high pressure, but bacteria out there do it for free. Yeah? So it would be really nice to simulate how they do it to come up with better tools to or questions around vaccine distributions, yeah, and so on and so forth. Yeah. Sorry, there's always a big delay. Yeah. Yeah, no, this is a nice project that I've been involved with. Try to model the whole sustainable food production system, yeah, on a quantum computer. You know, with climate change, you know, some crops don't grow anymore where they used to grow. So you need mention also the other aspect that I have mentioned so far that at some stage will be discussed in the school as well, which is the quantum effects in biological systems. Yeah? And this is also something that that goes back 70 years. Yeah, already in the 40s, Schrödinger wrote a book on what is life. Yeah, and this was long before DNA was discovered. Yeah, and he had already the intuition that maybe some kind of aperiodic solid, yeah, could be at the core of our genetics. Yeah, which I mean was a really good guess. Yeah. So the tradition of physics, quantum physics and biology goes way back a long time. Yeah. And what is really fascinating, and this is a slide inspired by Bethany, Bethany, thank you very much, is that, quantum biology, without going now into the details, yeah, it's really studying the quantum effects that lead to chemistry, which in turn leads to biology. Yeah, so it's really inevitable, if you want, yeah, to study quantum effects in biological systems. Yeah, because at the core we're all made of quantum stuff. Yeah, and simple quantum reaction, for instance, singlet triplet production, yeah, can lead to different chemical products, yeah, which in turn can lead to different biology. Yeah, so there are really strong connections from quantum physics straight to biology. Yeah. Okay, maybe let me skip the details. Maybe just mention a paper that we were very proud of, but nobody cares apparently. Yeah? Which was a very simple model that we, during the times of COVID, everybody had to do something about COVID. Yeah, and we did a really nice vibration assistance tunneling model of how the COVID virus attaches to the various receptors in the cell, yeah? And which had in principle also the potential of leading to some new ways of dealing with these problems. Yeah? But anyway, this is something that we're still working on a little bit on the side. Yeah, yeah. Coming back, I mentioned in passing the Shor algorithm for factorization. Yeah, and that is the problem that is at the core of our internet security at the moment. Yeah, most cryptographic protocols use something like RSA, yeah, which is essentially based on the mathematical difficulty of finding the decomposition in prime numbers of a large number. Yeah, yeah. And that is what Shor can do easily. Yeah. So the problem is should be worried now. Yeah, that maybe a future quantum computing can crack our standard security. Yeah, and the answer is yes. Yeah, for the very simple reason that you can store now encrypted data that you can easily steal from optical fiber network. I just need to bend a little bit of fiber and everything comes out, and you can read it like a book. Yeah, and when you have the quantum computer, you can then open it up. Yeah, so the time where quantum computing might be a threat really depends on how long you want to keep your secrets, yeah? And how long you think you can migrate to what we now call post-quantum cryptography. Yeah? So some institutions, they might have already a big problem now, yeah? Because people might have already downloaded their encrypted data and they just wait for the technology to improve to read them. Yeah. In South Africa, we don't have a quantum computer, the hardware in the country. There might be, for instance, in the quantum optics lab of our colleague Martin, he has maybe a 3-qubit photonic something, yeah? But it's nothing that that scales up to hundreds of fault-tolerant qubits. Yeah? So this is one of the battles that we want to win. Yeah. What is worrying us is now that there are already export controls on quantum hardware. Yeah, so that's why we need to start thinking maybe one day to build our own. Yeah, yeah, because we don't want to be cut off. Yeah, we are involved mainly again for the young students. Yeah, with you mentioned QWord. Yeah, this is one of our standard partners. We have a South African quantum technology initiative that also has bursaries for masters and PhD students and another way of supporting. Yeah, we have the National Center for High Performance Computing, which is the institution that gives us access to quantum computers. Yeah, at the moment they have an agreement with IBM. So through the National Center for High Performance Computing, every university in the country has access to IBM quantum computers. Not unlimited, but of course, certain, like every other project on the CHPC, you need to upload a little project description, what you want to do, and blah, 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 and then they allocate you a certain computing time in the IBM cloud at the moment. Yeah, we are also connected to the Open Quantum Institute in Geneva, and we try to exploit all the tools that we have. Yeah, maybe just to come to an end briefly. You know, I mentioned a few Nobel Prize winners over the years. Yeah, and then with ChatGPT research, I asked him to do the statistics for me of 4 Nobel Prizes that have something to do with quantum. Yeah, and this is the statistics. You see, in the 20s, we mentioned a few, in 50s and 60s, that's the years of technology, yeah, lots of them. Now we have again lots of them, yeah, because of the second quantum revolution. And on average, there is one every 2.5 years. Yeah. So for the youngsters, so if you get involved in quantum science and technology, the chance of getting a Nobel Prize is quite high. Yeah. Okay, so this was my 2 bits and pieces to the World Quantum Year and the World Quantum Day. Yeah, and I hope that this inspires a little bit what we have to do the rest of the week. Yeah, so thank you very much. Yeah. Very.
So just make sure to use the mic in front.
Yeah. Yeah, sorry, no, so that the people online can also hear. Yeah.
So on that last plot, was that Nobel Prizes including per person?
Yes.
So for example, the last one had 3 people. So
yes.
3 in the history.
Yeah.
But it's only 2 though in the.
No, this is just these just Nobel Prizes. Yeah.
Yeah. So the group of 3 people counted as 1 prize.
Yes.
Not 3. I think it should be 3 prizes.
Okay. I can redo the statistics.
And then it looks even more impressive.
Yes.
I think, especially recently.
Yeah. Okay. Point taken. Yeah. I will complain with ChatGPT. Yeah. Camille. Sorry, let me give you the.
Should I press something?
No, I think it's open.
Okay, wow. Just continuing on Nobel Prize. Who do you think would be the next Nobel Prize in quantum?
You.
Okay.
No, I don't know.
Yeah, it's difficult to know. But
Difficult to say. Yeah.
all right.
Difficult to say. Please.
Very small mic.
I hope this works. So previously we've mentioned quantum assisting with food security and stuff within the world or the country. Can you name a few initiatives and ways in which quantum has helped specifically with food security?
Yeah, none so far.
All right.
You know, the effort is to try to attack some of those big problems, yeah, and show that there is some kind of advantage in using quantum computers. Yeah, you know, people do it with classical computers. Yeah, and we just try to find the right formulation to run it on quantum computers. Yeah? But so far, it's just trying to. Yeah, and we haven't had any particular advantage so far. Yeah, but there is hope. Yeah. Yeah. Okay, if there are no other questions, I think there's a coffee break waiting for us outside. Yeah, and what time do we start again, Graham? Yeah, maybe at 11 we start again. Yeah, perfect. Yeah, then thank you very much.
Just give me a second.
Very much. Thank you, Cavaliere Francesco. I'm not famous. Francesco is, but he always says that I'm famous and everybody else is, but that's not the case. But I am here, and I'm glad that I can talk to you about open quantum systems. That's a huge field, right? Say open quantum systems, and you go, I don't know, online and you check open quantum systems, you find hundreds of books, thousands of papers. You know, people have been working for many decades on that. People are still working on it. And I work on it, have been working on this for maybe 2 decades. And I'm at the university, I'm in the maths department actually, at a university in Canada. Memorial University is called. And it's on the very east coast of Canada. Canada has provinces, and this is in the province of Newfoundland and Labrador. It's the most eastern province of Canada. In fact, when I fly, I mean, Africa is a huge continent, but Canada is a big country as well. So if I fly from where I live in St. John's, in this, the city is called St. John's, where my university is. If I fly, that's on the west side, so on the right side of my country. If I fly to the west coast of my country, the distance is bigger than from me to Central Europe. Okay, so it's also a very big country, Canada is. And we are coming out of winter in terms of weather. We're going into winter in terms of economy, I think, but we all do somehow. And so it's nice to be here in almost summer. Anyway, it's fun to be here. Thank you for inviting me. My lectures are in several parts. I don't know how far I will get today. I don't think it's very important that I rush things at all, because I don't know you, I don't know your background. So the ideal would be that I'm like talk about stuff, and that if something is unclear or you want some more information about whatever it is, definition of objects or anything, as easy as you think it should be. And if you don't know it, just interrupt me and ask. And then I will try to use, I can write on this here, or I can use the fancy whiteboard, and then we can just clarify things a little bit. Okay, we're not in a rush, if that's okay for you. And okay, sorry, but I just think, ask questions, ask simple questions. Like, okay, so you're students, but soon you will be giving talks at conferences and stuff when you're a bit later. And people always think, if I want to impress people, I have to give very complicated talks. It has to be very intricate and complicated and stuff. It's the opposite. The easier and simpler you do things, the more you impress people, okay? And so if you ask a very simple question, I and the older people in here, including me, will be very impressed. We should ask simple questions and not be ashamed of any question. Okay. So you can approach this open quantum system theory on a very abstract level if you want, but we have a limited time here. And so I thought what I will do is I will talk to you, I will do it by an example, kind of. I will treat this James Cummings model, which is a very famous model used, for example, in quantum optics, and I will use the open version of the James Cummings models. All of the models, as simple as they are, you can take the simplest models in open systems, and except for very few exceptions, which are physically not so relevant, I believe, they're not, solvable. You can't, solve the thing, write down a formula, you know everything. No. the very nature of open systems, which are systems that you're interested in, but they are embedded in noisy environments. The very nature of open systems is such that you cannot deal with them analytically 100% correctly without making approximations. And so lots of this theory of open systems is what kind of approximations can I do? How good are they? When are they valid? And stuff like that. Okay. Now, formalism of quantum theory. I have a few slides where I just recap the very basics for you. Okay, so there's the concept of a state, right? A state is what Francesco called a wave function. Is this object psi, it's a vector, and it belongs to some Hilbert space. Okay, that's abstract. But depending on what kind of physical system you want to look at, you go to your favorite physicist friend and you tell him, okay, I would like to describe a spin that can be up or down, or a qubit, which can be 0 or 1, or a particle that can be between two locations spatially, either here or here. Okay, so 2 degrees of freedom. Then the physicist tells you, okay, you should take for a Hilbert space to describe this, the Hilbert space C2. That's sort of the easiest thing you can imagine. If you want to describe a particle, and this is what Francesco mentioned as well, then the state is given by a function which is in a Hilbert space of square integrable functions, L2. Okay, and so this is psi will be a function, psi of x. X is the position. Okay, and that is really where the name wave functions comes from, because it describes a particle or a wave in space. And then you can do any kind of physical system you want to describe. For example, if you want to describe the quantized electromagnetic field, then your physicist friend will tell you, okay, yeah, there's a Hilbert space describing that, and states in this, states of the system are given by vectors in this Hilbert space, and they would tell you that for the electromagnetic field, for example, you take something called Fock space. Okay, not that this is very important what these things are right now, but I'm telling you that people know which physical system should correspond to what kind of Hilbert space, because of course Hilbert space is a concept, an abstract mathematical construct. And then there is a postulated quantum theory that tells you, well, if I have, let's say, a qubit here and a qubit there, but now I'm interested in looking at them as a unit of 2 qubits, then the question is, how do you combine this? How do you combine subsystems? How do you make them together into a bigger system? And the postulate of quantum theory is you should take the tensor product of the corresponding Hilbert spaces. Okay, so if one qubit has Hilbert space C2, so a state is given by a vector in C2, that's just a vector with 2 components, then 2 qubits belong to a 4-dimensional Hilbert space C2 tensor C2. And if you have an n qubit register, then you have to take the corresponding Hilbert space to be n times the tensor product of the individual guys. But the objects that you combine together, of course, don't always have to be the same. You could ask, well, what happens if I have a qubit or a spin that is actually exposed to electromagnetic radiation? All right, well, then we knew from before, the qubit is given by C2, the Hilbert space. The radiation has Hilbert space, Fock space, and the postulate then tells you this combined system has a Hilbert space, which is the tensor product of the 2 individual guys. Okay? In fact, this is sort of something that we will deal with in this Jaynes-Cummings model. Okay, then you want to observe things. You want to observe and measure things. And the third postulate of quantum theory tells you that each physical observable corresponds to a self-adjoint or Hermitian operator on your Hilbert space. And if you know what you want to observe, energy, position, momentum, angular momentum, whatever, and you have your corresponding observable, then you can ask yourself, well, what is the possible readout that I make in an experiment where I actually measure this quantity on a given system. And the postulate of quantum theory tells you, you can't get just anything, but if you look at your operator, which corresponds to the physical observable, then this operator being Hermitian, or I call this self-adjoint, okay, then it's diagonalizable, it has eigenvalues, and whenever you make a measurement, the only possible outcome is one of these eigenvalues. Nothing else is possible. Okay, and that's the crazy thing in quantum theory. If you take a bunch of states which are all exactly the same, and generally you measure a quantity like the energy of the state, you get a readout which is one of the eigenvalues. But now you repeat the measurement, the same thing. You take the same state, you make the same measurement. Oops, you can easily get another readout for the energy. So this measurement process is statistical, it's random, and quantum theory tells you with what probability you will get what outcome. And the fact is that the statistical average of what the outcome is given by this quantity here. You take your operator A, you apply it to your state psi, then you take the inner product with psi again, an overlap here. This is going to be a real number because A is Hermitian, and that is the average of the outcome of your observable, of your measurement. There's a more detailed way of saying what exactly is going on, but we won't need that. Okay, for example, in the situation of a qubit, this acts on the space, the Hilbert space is C2. So, you know, elements, wave functions are given by vectors like this, A, B, actually they're normalized. And so observables are 2 by 2 matrices, Hermitian. For example, if you take this Hermitian matrix, it has eigenvalues 1 and 0. And so the only readout you can get when you make a measurement according to this observable is 1 or 0. And that would be the value of the qubit. It's either 1 or 0, okay? And you know, if a particle is moving throughout space, then you want to measure its position. Then the operator is the operator which is a multiplication by the variable x. And the momentum is given by the gradient operator, or simply the derivative in one dimension, okay? All right, so there is one more postulate of quantum theory, and it tells you how things move. Right, in any theory, you should have an equation of motion to see what's happening and hopefully predict what's happening. Right, if I know my system right now and I know the environment it is in, I want to know what does it do in 10 minutes. Okay, and in quantum theory, well, of course, the dynamics is given by the very famous Schrödinger equation. Kind of, as we will see. Anyway, the Schrödinger equation is this differential equation. I is the complex, what's it called? The imaginary unit. H bar is Planck's constant. And I will just, I hope the very fundamental physicists will not be mad at me that I will set this constant equal to 1. You can just rescale energies and then this is 1. But anyway, so modulo this constant, which is imaginary, you have to take the derivative. So psi now, the state, will be a time-dependent thing. For each time t, you get a vector in your Hilbert space. So you get an orbit in your Hilbert space for the dynamics. And this orbit has to do this. If you take the time derivative, you have to get the right-hand side, which is a special operator h applied to psi. And the meaning of the special operator h, which is called the Hamiltonian, is it is the energy, observable of energy of the system. Okay? Formally, if you integrate this equation, this is the solution. Okay? For time equals 0, e to the 0 is 1. So you have psi at time 0 is the initial condition. And then as time evolves, you just simply apply this unitary group in t to the initial condition, and you get your state at time t. Okay? This is the Schrödinger equation. And it works for all systems, you know, for qubits, for particles moving. It works for qubits interacting with the electromagnetic field alone, and so on. But often, you know, you are interested in only a part of a system. For example, maybe I place, whatever that means, I place some qubits on a table. And these qubits, well, they interact with the table because, you know, they have to sit on the table, and I go like this, and there will be noise affecting the qubits, and they're immersed in light and so on. But I'm only interested in the qubit alone. So the question is, I don't want to always, by looking at anything I'm interested in, I don't want to have to know everything about the whole universe because everything is interacting. I just want to know what happens for a subpart of some system of a system of interest. Okay, and it turns out if you're looking for the reduced, it's called reduced equation of motion of a subpart of a system, then the correct equation is not the Schrödinger equation. The Schrödinger equation is correct for so-called closed systems, that is, systems that may have interaction inside of it, right? But systems that do not talk to exterior parts. Okay, so what is the reduced state and the reduced dynamics? Again, reduction means I have a complicated whole system, but I'm only interested in part of it. Okay, so according to the principles of quantum theory, the Hilbert space, let's say it's bipartite. It has a system part and HB, S for system and B for what people call, I guess, bath. So it's a system that's immersed in all kinds of noisy effects, and that is characterized by a bath. And so the Hilbert space is like this. And you have a state of the full system plus reservoir or bath. That's a vector according to our previous principles in this Hilbert space here. If you have heard about entangled and not entangled vectors, this vector doesn't have to be of product form, so it's not generally of the form psi s tensor psi b, where each of these would be in the respective spaces, but it's in general a general element in here. It could be entangled, okay? And now, so here's the picture, right? Here's the whole system plus bath. Here's the system alone. And I only want to make measurements, let's say, of observables which act on the system. I don't care about the degrees of freedom of the bath, because whatever, this is the stars and something I'm not interested in, okay? And so if I make a measurement on the system, well, I will have to take a system observable, which is a guy, a bounded a Hermitian operator acting on this part of this of the whole Hilbert space only. And so if I want to look at the average outcome, I have to take the observable, which is of this form, because I only measure on the system. I don't measure anything on the reservoir, which corresponds to put here the identity matrix. And I have to take this overlap here in the full Hilbert space. And that is the outcome, the average outcome of the measurement on the system alone. But see, the left-hand side here still involves the full Hilbert space, even though kind of trivially in the sense that the observable doesn't act non-trivially on this part of the space. And if you wish, you can say, okay, but the mapping that looks at an input A and maps this to this number is a linear functional on the operators of the Hilbert space. Okay, and as such, if you know a bit of mathematics or linear algebra, you will always be able to find a unique object rho. We will see what this exactly means. A unique object rho, it's actually also a matrix, so that if I take rho times A, and this rho only acts on the Hilbert space of the system, and if I make the product of these two matrices and I take the trace is of a matrix, right? It's the sum of the diagonals. Then I get a number, and this number is actually equal to the outcome, the average outcome of the measurement. So the left-hand side involves the system and the reservoir, because the state psi is in this tensor product Hilbert space. You have to take here the inner product of this bigger Hilbert space. But the right-hand side doesn't make doesn't involve the reservoir, the bath Hilbert space explicitly. Everything is encoded in this row. And this fabulous object rho has a name. It's called the density matrix of the reduced system. So apparently, if you look at only part of a big system and you try to describe what a state is, then you cannot just look at vectors psi in the Hilbert space of that system. No, you have to look at something else. You have to look at these density matrices. Okay, this is also called a reduced state. And what are the properties of this density matrix? This density matrix is simply defined by this relation here, okay? You can quite easily figure out the following. The density matrix is self-adjoint, meaning that it's equal to its adjoint. Oh, okay. So I might sometimes, when I put star for an operator, it is the same as dagger for physicists, okay? It's the adjoint of an operator. It's complex conjugate transpose of a matrix. Okay, so you figure out that this rho must be a non-negative operator, so it is self-adjoint, and a matrix being non-negative means that it has only non-negative eigenvalues. Furthermore, it has to have trace equal to 1. And it can be obtained as the reduction of the full, because this is in the full H system tensor H bath Hilbert space. If I take this and I look at the rank 1 projection, I hope maybe you have seen before this Cat-Bra notation. This is the orthogonal projection that projects onto the subspace, one-dimensional subspace generated by psi. Okay, I take this object, which is a rank 1 projection in the bigger space, and if I take what's called the partial trace over the reservoir degree of freedom only, then that's how I obtain this rho. Okay, does this make sense? I know it makes sense to you, Camille. Do you have any questions?
Can you just repeat in the top line, the A and rho are both in the Hilbert space of the system?
Yes.
Okay.
That's the whole trick of this situation here. So the thing is, I have a big system, but I'm only really interested in part of it. And the question is, how can I find an effective description of only the part of it? So I do not want to involve the Hilbert space part of the bath. I only want to involve the Hilbert space of my system I'm interested in. And mathematically, the right-hand side only involves quantities on the Hilbert space HS. Everything that, all the influence of the reservoir of the bath on the subsystem HS, which I look at, is all of it is encoded in this row. So you can imagine, right? Of course, then, even if this psi is a very simple, if this psi is a relatively simple, let's say, state of system plus reservoir, once I do this procedure of reduction to the system alone, I might get a quite complicated row because it has to include all the environment effects, okay? So row is generally complicated, and I think one of the core tasks of people working in open quantum systems is to figure out, I haven't talked about dynamics yet, but of course, if psi is a time dependent, then this rho will also be time dependent, and you get an evolution equation for rho of t. What is it? It will be complicated because it has to incorporate all noise effects onto the system. Okay, so you reduce your world to only the system, but things get more complicated. The notion of state is more complicated. The dynamical equations are more complicated. Of course, they have to be, because they must have all kinds of noise effects in their description. Okay, so we should revisit our notion of what a state is if we're not only interested in isolated systems. And so a state for us now is a density matrix that's a non-negative operator. Interestingly enough for you, for those of you who are interested in linear algebra or mathematics, saying that an operator rho is non-negative implies automatically that it must be Hermitian. But anyway, so rho is a non-negative Hermitian operator. It's normalized as having trace equal to 1. I didn't tell you to begin with something. When I introduced states, they're actually supposed to be vectors. These states psi that I had before, they're supposed to be vectors of norm 1. That's for probability reasons, you know, probabilities have to add up to 1. And this is reflected in the fact here that the trace of the density matrix has to be 1. And if I'm interested in the average of measurement outcomes of an observable A, simply I have to multiply rho with A and take the trace of this thing. I get a real number, which is the average of the outcome. Yes?
What would you mean physically if that condition, if it's 0?
If rho is equal to 0. You mean if this is equal to, oops. Sorry. This here?
Yes.
Okay, well, that's a good question. If the operator is 0, so think of it as being a matrix, right? It is the 0 matrix, 0, 0, 0, all elements are 0. What's the trace of that?
0.
Yeah, is it a state? No, because the trace of a state has to be 1. You see, this bigger than or equal to 0 is meant in a, that's a relation on, how should I say that? It's a relation about operators. So you can have a matrix that has certain eigenvalues 0, certain eigenvalues not 0, okay? That is a perfectly good example of a rho which is bigger than or equal to 0. What this says is simply that if you look at the eigenvalues of this matrix is Hermitian or self-adjoint, so the eigenvalues have to be real. So what this says that all the eigenvalues should be bigger than or equal to 0. But if you say, if I take this equal to 0, that would mean that the operator is equal to 0. That means all the eigenvalues are 0. That is not a state, because the trace is not 1, okay? All right, so what's the
statement? It's a statement about the eigenvalue, it's not the rho itself.
In a sense, yes. Okay, the spectrum has to be non-negative, okay? It's just saying what is a non-negative operator. So if you have, maybe I shouldn't call it rho. Let's say you have an operator O. It's a matrix, let's say. O bigger than or equal to 0. One of the most pleasing definitions is if I act with this operator on any state, on any vector x in my space, and I take the overlap with x, I get something non-negative. This is equivalent to saying that O is Hermitian. And the spectrum of O is in 0 infinity. So yeah, I guess it's only about the spectrum. Okay. So what is the evolution of the reduced state? Okay, I told you that the reduced state is obtained. Okay, so people also call a wave function or a normalized vector in the Hilbert space, they call it a pure state sometimes, and these rho are called generally mixed states, okay? And the mixed state is the reduction of a pure state from a bigger system to a smaller system. So as I told you, what if this guy evolves according to the Schrödinger equation, right? If this evolves, this psi of t is e to the minus I t h psi of 0, then for each time t, you have this thing here. For each time t, you take the partial trace, so you end up with a density matrix rho of t. And the question is, what is the evolution of this reduced state? Again, this is the recipe. You know what the evolution of the full system plus path makes pure state is, because that's the Schrödinger equation. It's given. But what does this mean for rho of t? Here is what it is. That's what it is. And if you study this, then you are in for some not so good surprises. The first one is, you see, before I take the reduction of the full state to the subsystem, this is the evolution. It's kind of easy, right? Because I take the initial state, and all I have to do is conjugate this initial state with this unitary group on the left and the right. Of course, on the left, it's with a plus, and on the right, it is the adjoint, which is with a plus sign here and the minus sign here. But anyway, so the dynamics is encoded entirely in this guy H here. Of course, because this guy H is the input, the only input in the Schrödinger equation. So if I have full control over the Hamiltonian, I know everything about it, which means I know all the eigenvalues and eigenvectors, then I a priori know fully what's going on here. But when I take this partial trace of this structurally easy situation, if you wish, I do not get out something of the form initial state of this guy and then conjugate it with some wished for effective maybe Hamiltonian. No, this is not of this structure. You see, this here is a group in T. If I propagate from 0 to 10 seconds, I can first propagate it from 0 to 3 seconds, and then from 3 seconds, another 7 seconds to 10 seconds. But once I take this partial trace, it is not the case. The dynamics of the system is not of this form. That's because the system and the reservoir and the bath in the revolution, they exchange information, they become entangled, it's getting complicated, and taking this thing here sort of cuts this entanglement in a sense. Anyway, so it is not of this form. I have no idea. There is no HF like this, so I can't use any kind of technology. You know what I mean is analytic technology to potentially have an effective Hamiltonian, then study its spectrum, and eigenvalues, eigenvectors, and then know this. No, you can't. You can't even do that because the structure is not like that. Okay? So that's bad news. On the other hand, it's not that bad because, you know, this map T goes through rho of T is not totally arbitrary because it does come from a sequence of actions you take. Namely, you have an initial guy, you conjugate it with a unitary group, and then you take a partial trace. Okay? And as it will turn out, the fact that you do this, what I just said, gives this dynamics a very special structure. It's called a CPTP structure, completely positive and trace preserving map. Okay, and we will maybe tomorrow or the day after investigate what this structure is. Okay, so do you have questions?
Means old main holding.
Oh, Hof doesn't mean court?
No, in this sense, it means main.
Main. Okay. So the plan now is to look at this very specific model, which is actually an important model, kind of, and explore in sort of hands-on a little bit these concepts that I was telling you about. Okay, it's called the dissipative Jaynes-Cummings model. And what it does is it should mimic, it should model what's happening to an atom in a cavity where you can have a photonic field, so electromagnetic field. And there are various complications to these models, I guess. Well, first of all, what is an atom, right? How do you model an atom? Again, you go to your physicist and say, I would like to model an atom. What Hilbert space should I take? Then he tells you, well, that's not so simple. I mean, what kind of atom, right? So I guess the hydrogen atom is kind of the easiest one because it has not so many electrons. And he tells you, you have to do this, you have to do that. But then you say, oh, that's way too complicated for me. I'm going to want to model, at least in this setup, my atom by a two-level system, okay? Because maybe the atom is a complicated object, but you know what I'm interested in is like looking at only two states of the atom. One state where the atom is what we call excited, it has quite a lot of energy, and another state where it's de-excited. And even to only look at processes involving two levels of the atom. So I will just simply model the atom by a two-level system. Doesn't get easier than that. And the electromagnetic wave or the cavity, you know, it's like a tube with mirrors where you have photons traveling around. Those I will model with, well, bosonic degrees of freedoms, so harmonic oscillators. So I will take a bunch of harmonic oscillators. These harmonic oscillators, they are indexed by K. Yeah, you know, maybe I take K to be 1, 2, 3, 4, up to N. Maybe I take infinitely many eventually. In fact, it will turn out that you have to take not only infinitely many, but uncountably many for some stuff to happen. But for now, let's just not care about how many we have. Let's let them be indexed by this index K. And they are the usual creation and annihilation operators. And again, I'm sorry, this dagger and the star here, they're supposed to be the same thing. They have the usual bosonic commutation relations given here. That's the Kronecker delta. Did this make sense to you, right? You have seen this stuff before. I don't have, or I can explain, but good. Okay. We can talk about the harmonic oscillator if you want to. We don't have to. It is your chance to raise your voice now and say if you want that. And the two-level system, well, it has two levels. Okay, one level is called 1 and one level is called 0. So 1 is the one that has more energy and 0 is the one that has less energy. And there is an operator which is called the raising operator, and it's this thing here. What it does is if it looks at the ground state, which is this guy, right? If I apply the ground state to this operator, this is a vector of norm 1, so this is equal to 1. And so it spits out the answer excited state. So it transports the ground state into excited state, hence raising operator. And its adjoint, the dagger of this, is this guy. It's the lowering operator. If I apply this operator to the excited state, this overlap is 1 and it spits out the ground state. And if I want to act with the raising operator onto the excited state, Well, then since they are orthogonal, the inner product of 0 and 1 is 0, and I get the value 0, okay? Because I can't raise by more than one level. So these are the usual raising and lowering operators of a two-level system. It's kind of similar to this, except for harmonic oscillator, you can keep raising stuff, right? You can get as many excitations as you wish. Okay, so what is the Hamiltonian? So the harmonic oscillators are going to form this bath, this source of noise, and the atom is our system, the one we are interested in. Effectively, what we want to do is this. We want to have an initial state of the whole setup where the atom is in the excited state and all the harmonic oscillators, they're in the ground state. No excitation. And then we want to let these two objects interact and see what happens. And what we will see what happens is that, well, the atom will get de-excited in the course of time, and the excitation of the atom will be passed on to the field, to the harmonic oscillators. That's what we want to, that's the thing that we're going to describe. The interaction Hamiltonian is consisting of a part on the system alone, the energy of the system alone, the energy of the bath alone, and then an interaction term. What's the system Hamiltonian? Well, it is just given by this operator. Omega naught is, I guess, a frequency or an energy. And this operator here does the following. If you apply it to the vector, the ground state 0, you get 0. So one eigenvalue of HS is 0. And if you apply this operator to the other basis element, which is the vector 1, then you get the vector 1 back, multiplied with omega naught. So the spectrum, the eigenvalues of this thing is 0 and omega naught. So if you make measurements of the energy, you get either 0 for the ground state or omega naught for the excited state. Of course, we take omega naught to be a positive operator, a non-negative number. Okay, and the bath oscillator, so these are a bunch of independent oscillators. For each K, you have one oscillator. This is the number operator of the oscillator number K. Okay. And so you simply count. For each K, you count how many excitations you have. That's done by this number operator. And then you multiply this with the energy gap of the single step in the oscillators. Does this make any sense? Who has seen harmonic oscillators before? Barry has not. That's very bad. No. I meant quantum, sorry. Yes, right.
You can just give him the microphone.
I mean, you have to guide me a little bit. I don't know, you know, if all of this is, I mean, if you don't know what a harmonic oscillator is, then maybe we can talk about a little bit about it, because it's kind of the basic ingredient of this model. But you should tell me.
Maybe ask how many people would like you to do that.
How many people would like me to do that? Talk about the harmonic oscillator.
Nobody.
Yeah, but the reverse question will have the same outcome as an answer. Graham.
So the number operator, the B stagger B.
Yes.
That counts how many excitations of the gate level there is.
Exactly.
And we multiply the number of excitations in the gate level by the energy of that level, and that gives us sort of the energy for that level, and we add up all the energies for all the levels to get the.
That's right. You can also think. So let's say I fix a K. So operator number K, maybe number 1, number 2, it doesn't matter. Okay, so then I won't have this now in my notation anymore. Then there is, for this oscillator, what is the state space of this oscillator? What kind of states can this oscillator be in? There's a special vector which is denoted like this. It's called the vacuum, or the ground state. Okay, and this guy has energy 0. And then if the physical interpretation of this thing here, now K is fixed, like for the 10th oscillator, if I, to this vector, apply this special B star, which is called a creation operator, I create, there's no prefactor, right? I create another state, 1. This has 1 excitation. And so the oscillators can be in 0, state 1, state 2, because if I act on this 1 with another times B star, I create another excitation, 2, 3, and so on. So these are, if you wish, a basis of all the possible states or vectors in this Hilbert space of an oscillator. And they just tell you how much excited you are. And if each excitation comes with an energy of apparently, oh, nice, comes with an energy, what they call omega k for the kth guy. Well, if I have 10 excitations, then the whole energy of the state would be 10 times omega k. And this special operator, you can check, B star k, bk, if I apply this to the nth excited state, as I meant, then what you get is n times that vector. So this.
Can you move that a little bit to your right?
Sure. Like this?
Yes.
Oh, my right. Okay, sorry.
No, you would.
No, okay. I could also do this on my tablet, really, but anyway. So this operator, this combination of B star B, this is something you can check, I'm not going to do it, but if you apply it to the nth excited state here, what you get is the same excited state out, but multiplied with the number n. So this guy actually gives you in front the amount of excitations you have. Okay? And so if I multiply this guy with the energy of each step, well, then I get the energy of the Hamiltonian. There's another picture, right, where you say this is not excitations, but this is a number of particles. Like here I have in this oscillator, I can view it as a system of particles. Here I have 0 particles. Here I create a particle. So I have 1 particle, and this particle would have energy omega, k from k fixed. And then if I create 1 more particle, I apply to this state another time the operator B star k, then I have 2 particles, 3 particles, and each of them has energy omega k. And so the natural Hamiltonian, which counts the additive energy of such a thing, is, well, what's written here. This is 1 Hamiltonian, one oscillator, but I have many of them. And so for each one, I have to add up to get the total energy. Make sense? Okay, so you see, this here only acts only on the 2-level system. This here only acts on the path, on these harmonic oscillators. And so for something interesting to happen, so that there's an exchange of energy, correlation, whatever, in the dynamics between the two to make them talk to each other, you have to specify how they should interact. And a typical way that people do that is by specifying this interaction Hamiltonian, which has the form given below here. And I'm going to try to explain to you what this does. Okay, so there is the sigma plus. Let's first just look at this part. Forget about this part. Okay, so this part acts on both the system and the bath. Okay, on the system part, that's why you have here the tensor product, right? This is like sort of H system, which is C2 because we have two levels, times H bath, which is the Hilbert space of all of these harmonic oscillators. I didn't specify what it is, it doesn't matter here. Okay, but on the system part, you can raise the energy by applying sigma plus. But if that happens, what do you do? On the bath part, you do this. This B here is an operator which is given by that. You, for each oscillator, number K, you decrease the number of excitations by 1 because you apply to it the lowering, the annihilation operator. I'm quickly going over there again. For the régisseur, so what happens, I told you, you can raise the excitations by applying B star to a state, but it is also true that if you this is a prefactor, but don't worry about that. If I have n excitations and I apply of my mode number K, of my oscillator number K, I apply the annihilation operator, I get something proportional. There's a prefactor here, same up there, it's not important. I get n minus 1. So the action of B destroys one particle or destroys one excitation, while the adjoint, the action of B star, creates one excitation. That's why this is called a creation operator and this is called an annihilation operator. So going back to this interaction here, what it says is that if with this term you excite the atom, right? Because sigma plus is the operator that ups the energy. At the same time, you have to de-excite the oscillators. So this term describes a process where an excitation is going from the bath to the system, to the atom, because the bath uses an excitation and the system gains an excitation. Okay? And the opposite process can also happen, and it's described by this term here. Here, the atom will lose an excitation because, you apply this lowering operator, but at the same time, in the bath, you have here the star, which is the adjoint. You have here, you create in the oscillators one excitation. Okay? So this interaction Hamiltonian is able to describe interactions of excitations between the system and the bath. Okay. Make sense? Okay. So our task would then be, well, look at this system. You have now a Hamiltonian. That's it, right? I know the players in the game, these oscillators, the two-level system. I have their Hamiltonian. Solve the dynamics. That's the task. So the Schrödinger equation of the whole complex atom plus bath is given by this here. That's just the Schrödinger equation. And one thing to make things look a little easier, but it's equivalent, is to pass to the so-called interaction picture. You see, how should I say that? This is always the case in open system theory. Most always. You have this situation, okay? You have an easy part, a non-interacting easy part of a system because of a complex, I should say, because the system evolves alone. It's given by 2 by 2 matrix, very easy. Each oscillator evolves alone, given by simply this, very easy. But then you but this is easy, but it's also uninteresting because system and bath don't talk to each other. But then you have to make them talk to each other, and that's where interesting effects will happen. But the price to pay is that the Hamiltonian now has become complicated. So we can safely assume that we know everything about H0 alone, but if I add the HI, then things get complicated. And so when people say they pass to the interaction picture, they do the following. They say, instead of looking at the state psi, which would be the solution of this full Schrödinger equation, right? I look at a different function. I look at this blue phi here. It's what I'm actually interested in, like the true dynamics, but I multiply it, or how should I say, I propagate it with inverse time with respect to the easy free dynamics that I know. Okay, so again, I really want to know about this. But then I say, okay, I want to know about this, but how about I look at this whole thing applied to this here? This is easy. Whether I have this here or not, in the end doesn't matter, because I can control this very easy because it's generated by this non-interacting Hamiltonian. And out I get this modified wave function of the full system and reservoir complex. The advantage is, if I look at this, the Schrödinger equation, or the equation that follows from the Schrödinger equation of this guy alone, the equation that follows for phi is a little bit simpler. If you take the derivative of this, because you have propagated in negative time direction here, which is not, anyway, you stick this in here, you see that the equation for phi is this below here. So instead of the full Hamiltonian H, you have what's called here the interaction Hamiltonian. The interaction picture Hamiltonian. You just stick this in here, that's what pops out. And so for phi, in this interaction picture, this is the Schrödinger equation, okay? The simplification is that, well, this HI doesn't have the free part H naught anymore. You see, it's just the interaction part, this guy here. But, well, it's a little, the price to pay is that you have to take this interaction Hamiltonian and propagate it freely, so it becomes time dependent. But again, this here is easy. In fact, for this model, you can calculate just explicitly what this interaction picture Hamiltonian is. I will scroll up again. Let's look at this here. This is one part of HI. This is the same part. It's actually the adjunct of the first part. Okay, it's sigma plus tensor B. The free evolution generated by H naught on both of these is very easy to calculate. I didn't actually write the procedure. I mean, I didn't write down how to do this, but it's very simple. And when you do that, then you realize it's the form given here. Just a second, this, to be precise, not that that matters. This is the free evolution of the sigma plus part. It's simply the sigma plus original guy multiplied with a phase, e to the I omega t. And the free evolution of this field here, B of t, is the same thing we had before. That was B when there was no t, no free evolution. But if you have a free evolution, you simply have to multiply each of these modes or each of these BKs again with a phase. Okay? The good part, once again, is that in this picture, H is just a single operator, while above here, the H was H naught plus H interaction. It is equivalent. You can do it either way, but it's just sort of the number of terms reduces if you go to the interaction picture. Okay, so we are going to try to solve, whatever that means, this equation here, and the reduction of this to the atom alone. Okay, it is equivalent to getting the original problem because the passage from phi to psi is easy because we know this explicitly. And the thing that saves us in this, that makes actually anything that makes an analysis possible here, is that the total number of excitations here is conserved. Think about it. These terms here, right? I told you what they do. So either you destroy, here you destroy an excitation in the atom and you pass it on to the system, sorry, to the field, to the bath, to the harmonic oscillators, or vice versa. You steal an excitation from the oscillators and pass it on to the system. But the sum of all excitations in the system and the reservoir are the same. They can just pass from one to each other, but they're never lost if you count the excitations of both together. This means that the Hamiltonian commutes with the number of total excitations operator, this n here. This n here, this is the number operator for the system alone. If the system is excited, it spits out number one excitation. If the system is in its ground state, it spits out value 0, no excitation. And this is already the guy we have encountered. It adds up the number of all excitations in all the springs, the quantum springs, which are these oscillators. You might have. This notation means commutator. So brackets Hn means Hn minus Nh. As you know, a fundamental thing in quantum theory is that it's a non-commutative theory, observables. And like in classical theory, they're not objects which commute. Of course, 3 times 4 is 4 times 3, but a matrix A times a matrix B is not the same as a matrix B times a matrix A generally. And so generally, matrices don't commute. But for the physical reason I just told you here, the number of total excitations is conserved, which means that this operator commutes with the Hamiltonian. It would be a good exercise to actually check this out explicitly for you. What this means in turn is that if I start off with an initial condition, let's say, which has 0 excitations. So the system is in the ground state and all the harmonic oscillators are de-excited in the ground state. Total amount of excitation 0. And I apply e to the IETH to that, nothing will happen. You will stay in the state of 0 excitations forever. Boring. Okay? If you have 15 excitations total, maybe you start off with the system having, well, the system can only have 0 or 1 excitations. But maybe then for 15 total excitations, you would start off with the system being excited. And 14 of the oscillators would be in the first excited state. Or one oscillator would have excitation number 14, so that the total is 15. If that happens for the initial state, and you look at the dynamics, you will stay in that manifold of total of 15 excitations. Okay? That's the symmetry of this of the Hamiltonian that does this job for you. And this makes an analysis sort of doable. Until when do I have? I forgot. Until 12:30?
Yeah.
Sorry?
Yeah, around 12:30.
Okay. Actually, what this means, for, if you're more interested in mathematics, well, whatever. This Hamiltonian H can be written as a block diagonal matrix, and each block corresponds to a spectral subspace of the number operator. Okay? And if you start off with an initial state which belongs to one of these spectral subspaces of the number operator n, as I said, for example, 15 total excitations, then in the course of time, e to the ITH applied to this initial condition will always stay in that subspace. So then you have reduced your infinite dimensional problem to a finite dimensional problem. Okay? And what we are going to do is we're studying one of the easiest, I guess, non-trivial situations. We have one excitation to begin with. So how do we formalize this? Let's see. I will introduce the vacuum state of the field of the bath, written like this ket, vac. And it means that each of the oscillators is in the ground state. 0 total excitation in the bath. And I will write vector ket k in the bath. That that's the state where I take the vacuum, but I create one excitation in the kth oscillator only, and everybody else is still in the ground state, okay? I denote this vector by k. This doesn't mean I have k excitations, okay? This means I have one excitation at location k. The kth guy here would then have a 1, and everybody else would be 0, okay? And as I said, I'm interested in the situation where I have at most one total excitation. So if I have 0 excitations, that's the subspace. If you wish, that's the subspace of this n. This n has a spectrum, I mean, has eigenvalues. N equals 0, 1, 2, 3, and so on. You can also count the multiplicity of these eigenvalues if you want to. Well, it depends on the number of oscillators you have, but the ground state, n equals 0, necessarily has to be simple because everybody has to be in the ground state. If you have one excitation, you know, you have many different states with one excitation, so you get a multiplicity of this eigenvalue. Anyway, you could count those if you wanted to. So this state here is the lowest, is the ground state, is the eigenvector of n with eigenvalue 0. No excitation in the system, no excitation anywhere in the bath. Now, when n is equal to 1, so that's the subspace of one total excitation. Well, either the excitation can be in the system, and none of the reservoir oscillators are excited, so they're all in the vacuum, or you could have the excitation in any one of the oscillators, okay? So these here, as k varies from 1 to whatever number of oscillators you have, these span, these are a basis of the eigen subspace of n with eigenvalue 1 excitation, okay? And we're saying to begin with, we look at an initial state where there's either one photon in the cavity or no photon, but we place an atom which is excited in this cavity, or nobody's excited, okay? If that's the case, then the initial density matrix must be written as a linear combination of these guys, because those guys span the situation 0 and 1 excitation. So psi must have a component along phi times, this is times 0, that's the initial state, has a component along the total vacuum of everybody, and a component along the state where the excitation is on the system only, and components along each of the possible directions, so to speak, in which oscillator number k carries the single excitation. Okay, so these numbers, C0, C1 of 0, and D1 of 0, dk of 0, they're the coordinates of the initial state in the basis psi0, psi1, psi k of this manifold, which has at most one total excitation. And by what we just said, because if you wish, the Hamiltonian leaves actually this subspace invariant. If I apply e to the I t, whatever, this is in the interaction picture, e, whatever. If I look at the dynamics of this guy, because of the symmetry of the Hamiltonian, that is, it commutes with the number operator, at time t, the state will be of the same form, that is, again, expressible in the same, at most one-dimensional, at most one excitation manifold. And what happens is that only the coordinates can vary, okay? Now, C0 doesn't vary because, as I told you, if you start off with 0 excitations, then the Hamiltonian cannot create any excitation. So this is constant. So that's good, because now the whole dynamics, you know, a priori, what we had is each oscillator has an infinite dimensional Hilbert space, right? Because it can have as many excitation as you wish. And then I take a bunch of such oscillators, so I have even more degrees of freedom. How do I describe this? Well, because of this symmetry, if you start off with one only excitation, you reduce it to just finding two functions. Well, not two. The function C1 and all the functions dk for all k. But use it just to the problem of finding a bunch of functions. And if you know these functions, and we will get to know these functions, more or less, then you actually know what the dynamics is. And then if you have nerves enough, you go back from this interaction picture to the original picture, which is an easy transformation, and you have solved your problem. Okay. So that still is the full system of the atom in the cavity. And I'm really only interested in the atom alone. It will be given, because the atom is a two-level system, the state of the atom alone, which will be obtained by tracing out all the oscillators, will be a density matrix on C2. Why C2? Because I have two levels. So the recipe, if you remember, is take the pure state of the full system, which is given by this thing here, and then take the partial trace over the all the reservoirs. So sorry, over all the harmonic oscillators. And then what you get, because this is the interaction picture, you get a density, the density matrix of the system, but I also put an I here because it was obtained with this guy in the interaction picture. So you get the density matrix of the system in the interaction picture. It's got to be a 2x2 matrix. It's got to have to be a non-negative, and it has to have trace 1. Okay? And look, especially for you. Okay, exercise 1. I've prepared some wonderful exercises for you that I will share somehow. I guess Graham will know how to do this. That on a PDF file where you have a bunch of exercises, which you must absolutely do, but do not come and waste my time asking me how to do them. No, I'm joking. You should attempt them, and if you have questions, you can approach me and we can discuss. Anyway, I can represent this operator here in the basis of 0 and 1 of the system alone. Okay? And if I do that, because here I have the form of the phi, then I sort of have to figure out how to do this ket-bra operator of the total thing, and then take the partial trace, if you know what that means, over the reservoir, over the oscillator parts only. What you end up is, written in this basis 1, 0 as a matrix, you end up with this 2x2 matrix. Of course, this matrix will depend on the functions in question, like C and D and C naught. And what you're supposed to do in this exercise is, you're supposed to figure out this blue shape of the form of this row. Okay? And we still don't know what this C1 is. In fact, all that's left now is actually this C1. You know, there's also something. You know, you have also the information that this phi of t has norm 1. This sort of also gives a constraint between the C's and the D's. Anyway, this is part of this exercise. But that's why sort of these D's, they evaporate, okay? So very cool. And if you're only interested in the system dynamics alone, in the end, you only need to know this quantity C1 of t. You boil down everything to knowing one function of t, okay? We still don't know what it is, but what is the equation of motion, the evolution for rho s of I? Well, here it is given. I can take the derivative, and if I take the derivative, the time derivative, right, dt, then I take the derivative entry-wise. This C naught, it's constant in time. And so this only involves the derivative of C and maybe the modulus squared of C. Okay. Incidentally, sorry, coming back to this here, you see that the trace of this is 1, because the trace is the sum of the diagonals. And you have this here and 1 minus the same thing. So if you add them, you're left with 1. And this matrix is supposed to be Hermitian, right? Self-adjoint. So yes, the diagonal is real, sure. And the off-diagonal are complex conjugate of each other. For me, this bar here is the complex conjugate of a complex number. Even more, you see that the diagonals are non-negative numbers. Anyway, so there's an easy structure kind of, and all you have to do is hunt for this C1. Okay, so the equation of motion is given by taking the time derivative. This kills this 1 here, and it puts a dot or on this time-dependent thing, and it takes the derivative of that. And so that is going to be the equation of motion. You know, sometimes when you deal with similar problems, it's actually more instructive to know what the equation of motion is of a system than to actually know the solution of the equations of motion. Because sometimes the structure of an equation of motion is very telling and will help you, you know, guide treating other problems and stuff like that. So yes, we of course want to solve this problem, but we also want to figure out what kind of evolution equation is actually popping up for this rho SI. And I guess that's what I'm doing right now. I'm looking at the structure of the evolution equation for now. Okay, so we want to know what this C does, because again, that's the only ingredient here to know the evolution equation. Okay, and let's assume that C1 at time 0 is not equal to 0. Physically, what was C1 at 0? C1 at 0 was the amplitude in the initial condition with the state which has the excitation in the atom. So let's assume that initially, at least, part of the excitation is in the atom. So this number is not equal to 0. Okay? Then it makes sense, well, a posteriori, you will see that right now. Then it makes sense to look at this ratio. C dot is the time derivative, of course. C dot over C. At least this makes sense at time 0 because the C1 of 0 is not 0. And then it will make sense for all times, actually. So this object here is just a complex number because it's the ratio of two complex numbers and the bottom is not 0. So we are totally legal. And so this complex number has a real part and an imaginary part. And you give them names. For some aesthetic reasons, I guess, you call the real part -1/2 times gamma of t. Depends on t, of course. This defines gamma. And the imaginary part of this number, I don't know this number yet. I just know it's a complex number. The imaginary part, I call it -1/2 s of t. Okay? So this defines gamma and s. And now, if I knew gamma and s, well, then I could solve this equation for C, because it's just an ODE that you solve, right? A very simple ODE. The equation, you integrate this, gives a logarithm, this derivative of the logarithm, blah, blah. And the solution, C1, in terms of this real and imaginary part, is simply given by this equation here. You have to exponentiate the integral, the antiderivative of these two things, and multiply with the initial condition. That is, if you knew what gamma and s were. That's kind of nice, you see, because, well, as it will turn out, these gamma and s, they will tell you somehow how, you see, okay. So this gamma is both gamma and s are real numbers for each time tau that you integrate over here, right? So just imagine for a second that somehow gamma was roughly constant, whatever, okay? Then, and S as well. Then you would be able to integrate, then this would be gamma times T plus IS times T, okay? You would have this in the exponent. And so the meaning of this gamma and T is the following. It tells you how this coherence, this off-diagonal density matrix element here, behaves in time. And in the case I just said, where we just imagine for a moment that these guys would be constant, the gamma would drive, if it also has the right sign, namely if it was positive, would drive some exponential decay because it would be e to the minus a half t times gamma if gamma was constant. So it would drive some exponential decay, and the S would be some modulation, some frequency, how should I say, some phase, e to the minus essentially I times the number S times t. Okay, so the gamma and S, they will encode how these off diagonals of the reduced density matrix behave in terms of oscillations and decay. Okay, so then, fine. If I know now this, I mean, no, I don't know it, right? But I just rewrote it in terms of new variables, but at least here I have good interpretations of what this gamma and S is. I can stick this back into the equation of rho, and so I will get here terms that now will depend on gamma and S. And if you do that, well, you get this beautiful formula. It's just a substitution, okay? So now we have expressed the evolution equation of the reduced density matrix in terms of two quantities, which we sort of physically might have a feeling for, gamma and S, okay? And there is a fun exercise for you, number 2. You should take this simple form and make it more complicated. Why would you do that? But if you're still around towards my 3rd lecture here, then you will figure out why you should do that, okay? Because you will uncover a structure. It is a fact that you should prove in exercise number 2. Colors are kind of off. This looks blue in my notes anyway. That the derivative of this density matrix has actually this colored form here, this here. It involves again S, and it involves again gamma, but otherwise nothing except the sigma plus and the sigma minus, which were part of the original interaction, and of course the unknown quantity rho S. So this looks more explicit, I agree, even though we haven't yet calculated C1 or gamma or S, we will. But this here gives a structure in which, for example, the C1 is not there anymore. You just have the S and the gamma. And it will turn out, if we analyze things a bit further, even in much more general systems, that the structure of this equation is quite universal. Okay? So then finally, when you have, after you did this exercise, you remember, ooh, this was the interaction version of the reduced density matrix. Then you undo the interaction picture, which means you conjugate with this unitary group in the opposite time. And what you get is this beautiful formula, which has the following structure. The derivative of the quantity you're looking for, this is an operator, density matrix, is given by 2 parts. One part is written here, one part is written here. The first part is you have some operator. How should I call this? Maybe A of t, depends on time. Whatever it is, there is an operator A, and you have to take the commutator. This is the commutator, remember? So this is A of t applied times rho minus rho times A of t. There's a commutator part of some, you see, this is the original Hamiltonian, and this here is sort of an extra term you have to add to the Hamiltonian, which comes from the interaction with the reservoir. So you renormalize the energy of the system, of the bare system, by having to add this term here. Anyway, so there's this commutator term. It's called a Hamiltonian term. And then there's a second term here, which has in front some coefficient, this gamma. And then here, again, these are the ingredients of the initial interaction, sigma plus and sigma minus. And you have to conjugate your unknown quantity here with these guys, and then, you know, and then add a certain thing. This looks all very mysterious to you, but it's actually, again, and we will see that, it's of a very standard form, very standard form. It's called it even has a name, it's called GKSL, Gorini-Kosakovsky-Sudarshan-Lindblad form, okay? And instead of deriving this, you know, in all generality, which you can, I thought it would be a good idea to look at the system and sort of get this form in a very pedestrian way. Okay, so I propose that I will continue tomorrow here, and I will show you how to actually calculate these coefficients. So the message is, even simple systems, open systems like a qubit or a two-dimensional atom interacting with simple harmonic oscillators, if you look at the dynamics, this is not easy, right? I mean, like, hello, what's the solution to this? No idea, right? You have to, it's not obvious. You can't solve things, but there is a structure, and this is the specific structure is given here. And another thing that I hope you appreciate is that sometimes if you have, or like always, if you have symmetries, which was this number of total excitations which was conserved, you can use this to reduce very high dimensional complicated problems to lower dimensional problems where you have only maybe 1, 2 parameters like gamma and S here. And then you still have to hunt for them, but at least you kind of know what you're doing. It's not like, you know, you have infinitely many parameters. Okay? And so thank you for your attention, and we'll continue here tomorrow. Yes. You need a microphone, I think. This one doesn't have a light on anymore. Maybe it's dead.
No, Doc, I just wanted to ask, since you mentioned reduced density matrix, so from an algebraic perspective, or perhaps algebraic level, the moment that you speak about density matrix, one would think of the concept of separable. So I just wanted to ask, since we can find a reduced density matrix for the open system, does it mean that the open system then can be separable? If the open system can be separable, then in this context, what does it mean to say that the open system is separable?
Okay.
Thank you.
What exactly do you mean by separable?
Like separable, for instance, that means that we could find maybe a countable matrix in this context, but in the algebraic form it would be a countable set to actually reach that certain system. Like for instance, let's make an example. Let's say that in an algebraic context, like to say that real numbers are separable. That means that we can find a subset of that, which is actual rational numbers, which is a countable set to reach those.
Okay, so
real numbers.
Good question. Thank you. Okay, separable. If you think, and I think that's what you're maybe referring to, if you think of functional analysis, you have Banach or Hilbert spaces which have countable spanning sets. And then such a space is called a separable Hilbert space, right? So there's another notion of separable in terms of which has to do with entanglement. That's not what you're referring to, right? Okay. So it is very simple here. At least in this example here. The Hilbert space on which the reduced system lives is C2 here, right? And there is a fact of basic functional analysis. All finite dimensional Hilbert spaces are separable. Okay? So maybe your question is, in fact, you know, okay, well, in this example, it's automatically separable because it's C2, it's finite dimensional.
Okay.
In fact, I should have maybe said, in the very first postulate of quantum theory is that for pure states, this size, they have to belong to Hilbert spaces. These Hilbert spaces are supposed to be separable. Now, if I have a composite system of H system, tensor H reservoir, each of them has to be separable because they have to exist as systems themselves. And there is a known theorem saying that tensor products of separable Hilbert spaces are separable. So everybody's separable. And so if I take the reduction of whatever I do to one of the Hilbert spaces, by definition, it's separable because I don't create a new Hilbert space. I started off with that Hilbert space, okay? But anyway, in finite dimensions, you don't even ask these questions here. Good question, though. Yes. What else? Will you do the exercises? That's the question I had. Okay, so I guess maybe you really deserved some food now. Enjoy your lunch.